Okay, let's look at today's Leetcode daily challenge actually. Uh, so this is 30th of December 2020. So the question is game of life. The question is quite long, so if you don't really know what's the question talking about, please read the problem description. So basically, if you are aware of this actually, so you can go to Wikipedia and then you can search for game of life. Actually, then it gives you a very long description of the what the problem actually does. Or you can just go to YouTube actually. So I think YouTube has some very good material on game of life. If you go there, so you can see there are some simulations. So the game life itself is just it's a board. So you have a board, and then you have some initial configuration, and then based on the rules listed here, so you calculate the state of the next state of the board, and you do it step by step, and then eventually or it will stop, or it will just run in a loop actually. So this is I think if you read the Wikipedia article, you will see it's a Turing complete machine actually. So you can actually use some encodings, and then you can run any algorithm probably on this game of life machine actually. But that's not the point today. The point today is to given a board configuration like this, you need to calculate the next board state actually. So for example, like this, I think having an example, looking at this simple example 2, you have 1 1 1 0, and given this rule 4, so any dead cells with exactly 3 live neighbors become the live cell, and then so this 0 cell, it has 3 live neighbor, but itself is dead. But you can see the next step, this cell should be lighted actually, and then because because of this rule, and the 1 1 1 cells. So for this one, it has 2 neighbors, 2 neighbors. That are live, and then according to this, any live cell with 2 or 3 neighbors live on to the next generation. So that's fine actually. So it stays with 1. So you have to be very vigilant about which rule to apply to each cell. So you need to know that. So I think on the surface, the problem is quite simple, I would say. If you are allowed to make a new board, so then you can just initialize a new board with the same size, and then you can try moving the board over, moving and then you can try for each cell, you just calculate its new state based on its current state, and then you just fill the new board with a new cell or new value, and then you just return the new board. That's one way to do that, but the problem is the follow-up here is could you solve it in place, and I think that's the tricky part actually. So you need to think about. So I think we can start with so in the interview setting you can say, I would suggest you can tell the interviewer to say, I can implement it with new space with OMN space, and then I can just implement these rules as a code, and I think that's a pretty easy solution. And then ask if the interviewer has any opinion. Usually, I think he would ask you to do this in place. Then you need to think a bit more about how do we proceed with in place without actually allocating new space. And to do that, you need to be able to without allocating new space, the only thing you can work with is old board, right? Like you have this board, so you have to come up with some kind of like encoding so that you know what's the original board state, and then because if you just do it bluntly, then I think like because for example, if I change the number from 0 to 1 here, although this is fine actually, this is a small board, but like if you just change it here, and then if the board is larger and you just bluntly change it to 1, that won't work, because that this cell is also affecting other cells. For example, this 1 0 1 0 0 0 0 case, right? Like if you just change 1 to 0 and ignore and then in your first iteration, then it will impact other cells state actually, and then you won't have the correct answer for other cells, if you see what I mean. So I don't think you can do that. I think you need to come up with some clever encoding to say what's the original state of this cell, and what's the cell now, the value of the cell now, and then you do it in 2 iterations actually, and that's the idea, and then you get to the final next state of the board. So I can give you a quick example. So I have compiled this one. So what I'm gonna to do, the key idea here is you encode the cell from live to dead. So if a cell goes from live to dead, then you denote that value to be -1, and if the cell goes from dead to live, and then you denote that cell to be 2. You have an so you have the beginning of the board, you have an intermediate board, and then you have a final board, which is the next state. And then so let's give you an example. So 0 0 0 0 0 0, so there's nothing changed on the first row actually. So if you look at this cell 0, all its neighbors, it only have 1 live cell, so it cannot go from dead to live, so you keep it to 0. Similarly 0 here, similarly 0 here. And to this cell 1, you look at the neighbors here, all its neighbors, you count only 1 of neighbors is live, and according to the the rule of the game, this one should goes to apparently this one should go to 0 here, but instead of going to straight down to 0, you denote it to -1 to say so -1 means I was originally live, but now I'm dead. And then this one, this cell 0, you see it has 1 1 1, it has 3 live neighbors, so that one should goes to 2, because according to the rule, so you have 3 live neighbors, but it should goes should be changed to 1 in the final state here. But instead of going to 1 directly, you denote it to 2. 2 means I was originally dead, so I was originally 0, but now I'm live. I changed my value to 2. So you see the sun here, the sun -1 1 here, -1 and plus minus and plus here denotes your state in the final board, denotes whether you are alive and no and dead in the new board. But the value here denotes whether you are dead or alive in the old board. So for example, 1 means I was originally live in the original board, but 2 means I was originally dead in the new old board actually. So similarly, this one should be -1, this one should be 0, this one should be 1, because if you look at its neighbors, it has 2 live neighbors, so that should stay 1. And then this one should goes to 0. So the key idea here is to denote the live to dead cells to be -1 in the intermediate board, and then denotes the died to live cells to be 2 in the intermediate board. And while you are constructing the intermediate board, you should check your neighbors live or not by taking the absolute value of the board of your neighbor and check it against 1. So in this case, when you move to the number here, this one already changed to -1, but that's okay because here like its absolute value is 1, this absolute value is 1, and this absolute value is 1. You have 3 members. That's our that are live. So I think the idea is quite clear, I would say. If you are not really convinced, please take out a pen and a pencil and then try to emulate this algorithm. What I did here, I think that's okay. That's the idea. So now let's go down to implementation. So I think you need to be for in the interview setting, you need to be able to explain the idea quite clearly to your interviewer. So I would suggest you take out a pen and pencil if you are doing a virtual interview, and if you are on a on-site interview, you can just take out a pen using the whiteboard, and then you can explain the idea to the interviewer. The communication is quite key here, actually. The idea is not really that straightforward, although it's once you get it, it's quite easy, but if you don't, then it's quite difficult to get it, actually. So then let's get down to the implementation part, actually. So I think I've explained the idea. If you are not clear, please leave a comment. I can help you to get to explain the algorithm a little bit better. So now let's get down to the Python implementation. So this is another part which you are evaluated on, which is implementation. So you once you get the whole picture, and then you can start implementing. So I wouldn't suggest you to rush into coding because that's a bad behavior. That's a very negative signal in the interview setting. You need to be able to say, I'm planning to do this in words in English, and then after that you can only after you agree on what you have been what you will do, then you start implementing, and then once you get the interviewer's approval. So I think it's quite key here to say not strictly not jump to the coding part, but to discuss with your interviewer what you should do. Okay, now we have the implementation here, and so let's just walk through what's the implementation doing here. So we got the board's dimensions, and then either one of the dimensions is 0, then we just simply return, and then we iterate through the board. And so this is just simply getting all the board's neighbors, actually. So there's one thing to notice here is be careful not to count the board cell itself, and then once you counted the number, this is counting the number of living board neighbors. So as mentioned, you take the absolute value of the neighbor and check if it's equal 1. If it's equal 1, then that's a live number neighbor. So if board ij equals 1, then that means, and then the count is now in 2 or 3, then that means the board should this cell should go to died, actually. So then according to the rules, and then the board you set it to -1 to indicate that this was a live board, a live cell, but it's dead now. And if the board this cell is 0, but you have exactly 3 neighbors that are live, then you set it to 2. I didn't mention that, but I think that 2, 3, 4, like either number should work here. Actually, 2 is just a random number we pick, but we pick 2. So to indicate that this was a live, this was a live a dead cell, but now it's live actually. So you can print out the intermediate board. You can print out the intermediate board like this, but I will comment it out later. And then once you got that, then you can just use a sun, as we mentioned. The sun in the intermediate board indicates like if the board, if the cell is live or not in the new board, and then you can see the result is clearly correct here actually. And then if we just hit submit, it's accepted. So I think this is a quite interesting question because the naive, as always, the naive implementation is quite the naive algorithm is very easy to implement, but the difficult part is actually getting to getting the in place solution here and thinking about how we encode the board state in the intermediate board, and once we process the intermediate board, we can get to the new board actually. So if there's anything unclear, I can answer any questions. Please leave a comment, and please subscribe, please. Thank you very much.